Hey everyone, welcome back to the series. In the last video, we finished building the layer struct, and now it's time to create the matrix class. We'll be using this class to represent the weights between layers in our neural network. It'll handle things like storing 2D data, initializing values, and applying simple operations like scaling, exactly what we need for this project. Let's jump in and get started. We start with a header guard to make sure this file doesn't include it more than once. And here we say hash fndef matrix underscore hpp and hash define matrix underscore hpp, and we close it with hash indef. Now we bring in the necessary libraries. Hash include vector for storing the matrix, hash include std_except for throwing errors, and hash include random to fill our matrix with random values. Now we define our matrix class matrix. Inside the private section, we define a 2D vector called data to store our matrix elements. Private std vector double data, and then two variables, rows and cols, to keep track of its dimensions, size underscore t rows, comma, cols. Let's move on to the public part of our class, public. Next, we'll add a constructor to initialize the matrix with the specified number of rows and columns and set all the elements to 0. Here's our constructor, matrix, and it takes size underscore tr, comma, size underscore tc. Then we assign them to rows and cols, colon, rows r, and cols c. And inside the body we say data dot resize, and we pass an r, comma, std vector double inside parentheses c, comma, 0.0. This ensures that every matrix we create starts with clean 0 initialized values. Now let's add two simple but essential methods, and here's the first one. Size underscore t get rows const, and it will return rows. And next, size underscore t get cols const, and it will return cols. These two simple methods return the number of rows and columns in the matrix. Very handy when we're looping through the matrix later. Now we're overloading the parenthesis operator to access the elements like a regular 2D array. This operator returning a reference, so we say double reference operator parenthesis, and it takes size underscore ti and size underscore tj. And here we add a safety check. If the indices go out of bounds, we throw clear error. If I greater than equals get rows, or j greater than equals get cols, we throw std out of range, and we pass in this message, index out of bounds. Otherwise, we return a reference to the element. Return data square brackets I square bracket j. And here's the const version for read-only access. Const double reference operator parentheses, and it takes size underscore ti and size underscore tj const, and inside the body we do the same. If I greater than equals get rows, or j greater than equals get calls, we throw std out of range and we pass in index out of bounds. Otherwise, we return data square brackets I square brackets j. Now we're going to add a method called fill random, and here we say matrix reference fill random, and it takes double min equals -1.0 and double max equals 1.0. This will fill the entire matrix with random values between a minimum and maximum, by default between -1 and 1. That makes it perfect for initializing weights in our neural network. Inside the method, we start by setting up a random number generator. First, we create a random device, std random underscore device, and we're gonna call it rd. This provides a non-deterministic seed to help us generate truly random numbers. Then we create a Mersenne twister engine using that seed, std empty 19937, and we're gonna call it gen, and we passing rd with parentheses. This is a high-quality random number generator. It's fast and has a long period, making it great for most applications like neural networks. Now we define a uniform real distribution, std uniform underscore real underscore distribution with default data type, and we're gonna call it dist, and we initialize it with min and max. This tells the generator to produce numbers between min and max with equal probability for every value in that range. Then we loop through the matrix and assign each element a random value. For size underscore ti equals 0, I less than, inside parentheses, asterisk this, dot get rows, and plus plus I. And inside this loop, we have another one. For size underscore tj equals 0 and j less than, inside parentheses, asterisk this, dot get calls, and plus plus j. Then we say asterisk this, I comma j equals dist, and we pass in gen. And finally, we return asterisk this, which means we return the current matrix object itself. This lets us chain this method with others. Now we're going to add an overloaded asterisk operator to scale the matrix by a scalar value. Matrix operator asterisk, and it takes double scalar const. This method creates a new matrix where every element is multiplied by the scalar we pass in. The original matrix stays unchanged. First, we create a new matrix with the same dimensions as the current one, matrix, and we're gonna call it result, and we pass in get rows and get calls. Then we loop through all the elements and multiply each one by the scalar. For size underscore ti equals 0, I less than get rows, and plus plus I. And then for size underscore tj equals 0 and j less than get calls plus plus j. And result I comma j equals inside parentheses asterisk this I comma j times scalar. Finally, we return the new scaled matrix. Return result. Now we're going to add asterisk equals or times equals operator to scale the matrix in place. And here we say matrix reference operator asterisk equals, and it takes double scalar. This method does the same thing as the previous one, but instead of returning a new matrix, it modifies the current matrix directly. We loop through all the elements and multiply each one by the scalar, updating them in place. For size underscore ti equals 0, I less than get rows, and plus plus I. And for size underscore tj equals 0, j less than get calls, plus plus j. And then inside parentheses asterisk this I comma j times equals scalar. Then we return asterisk this, allowing us to chain operations if needed. Alright, that wraps up this video. Our matrix class is ready, and it's going to be a key part of how our network handles data and calculations. In the next video, we're going to use the layer.hdd file we finished earlier, along with our new matrix class to initialize the weights and biases for our neural network. If you are enjoying the series so far, make sure to like, subscribe, and hit the bell so you don't miss what's coming next. Thanks for watching, and I'll see you in the next one.